Okay, we're in chapter 2, which is chemistry. And a lot of people wonder, why are we talking about chemistry and anatomy? But it's because chemistry makes up all of those. Remember, we talked about cells are made of organelles and these macromolecules, and those macromolecules are made of many atoms. And when you're at the atomic level and the chemical reactions that occur, we need to know about the chemistry that does that. And so the human body and the food and all of our medications are chemicals, and water and electrolytes make up all our body fluids. So we got to learn a little bit about it, right? So you need to know that matter is anything that takes up space and has mass. And so the air around you is matter. Of course, that would be a gas. Whatever you're drinking is matter. It's liquid. And then your computer or your desk is a solid matter. A mass is the actual amount of matter present, and we can weigh that using gravitational pull on Earth. So your weight on the moon is going to be different, but the mass would be the same. So chemistry studies the composition, so like what it's made of, the properties of the matter, and how the matter interacts with other matter. And biochemistry, where we will focus, is the biological chemistry that involves macromolecules. So elements you've probably heard of, they are the simplest type of matter, and there's 92 naturally occurring ones. And if you start combining different elements, you have what's called a compound. Now, atoms are the smallest particle of an element that have the properties of that element. And so we have bulk elements, which is what mainly the body's made out of. So carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus are bulk elements. We're going to see these in our macromolecules. And then we have trace and ultra-trace elements that are not found as common. Now, we are going to talk about the particles of matter, the atom, and then the subatomic particles, the proton, the neutron, the electron. And then we'll look at what ions are, and they are electrically charged because they've gained or lost an electron. So if you gain an electron, you got something negative, so you'll be a negative charge. If you lose an electron, you'll be positive because you lost a negative. So think about ions and like attitudes. If you gain a negative thing, you're going to have a negative attitude. If you lose a negative thing, you'll have a positive attitude. And then molecules are particles formed by the chemical reaction or union of two or more atoms. And so here are those major elements and trace elements that you'll find in the body, and the percentage. Does it surprise anyone that oxygen is so high percentage? Remember, we're made of water, and so this is by weight. Oxygen's a bigger molecule than hydrogen. So even though water's H2O, hydrogen is very small and oxygen's much bigger. So we're mainly made of water, and of course we're breathing in oxygen, and so we're mainly made of oxygen as far as atomically speaking. So remember that prefix sub means below. So subatomic particles are our protons, neutrons, and electrons. And protons are relatively large particles, and they have a positive charge. And you might want to make a note, they're found in the nucleus. Neutrons are also relatively large, but they're neutral. They don't have a charge. They're neither positive or negative. They're also found in the nucleus of the atom. And the nucleus is not a specific thing. It's just a place inside the atom. And then electrons are very, very, very small particles relative to the protons and neutrons, and they have a negative charge. And so I mentioned that protons and neutrons are found in the nucleus, so where are electrons? They're orbiting around the nucleus in constant motion. And the number of protons, remember they're positive charge, equals the number of electrons in an atom, which are negative charge. And if positive equals negative, they cancel each other out. And that's why the elements and atoms are neutral. So let's look at this atomic structure of lithium. In the atom, the area of the nucleus, you can see protons with their positive charge and neutrons with their neutral charge. And then the electrons floating around in orbitals or electron levels. Now, the atomic number of an atom is the number of protons in the nucleus, and that each element has its own atomic number. So if you change the atomic number, you change what element you're talking about. And the way I remember it's protons that are important for an atom is I think about going to a pro football game and I'm looking for Adam and his number, and that helps me remember that. I don't know. You got to come up with something that works for you. Now, the mass number is also easy for me because if you look at this atom, the bulk of the stuff is in the nucleus. So that would be the mass. And so the mass is the number of protons plus the neutrons, aka, put in parentheses here, what's in the nucleus. So if you can remember that electrons aren't in the nucleus, the mass of the thing, if you were going to weigh an atom, if you will, you'd really focus on those larger protons and neutrons and not so much of the little bitty electrons floating around. So electrons don't really contribute to the mass. They're just so light, tiny, and moving all the time. Now, isotopes are atoms with different number of neutrons, but the same number of protons and electrons. So all atoms have certain elements that have the same atomic number, but isotopes have the same atomic numbers but with different mass. So that means they have the same number of protons. Their neutrons are what's different. Excuse me. So the most common isotope I think about is carbon, because you've probably heard of carbon dating. So the normal carbon is C12, but there's also C14. Oxygen has a few isotopes. There's 16, 17, 18. And these numbers represent their mass numbers. All of these would have the same number of electrons and the same number of protons. But their weight is different, right? Their mass is different because of the change in the number of neutrons in the nucleus. Radioactive isotopes are unstable, so they're constantly releasing energy, and we use them to detect and treat disease, as well as like carbon dating, as I mentioned. For any element, the atomic weight is considered the average mass number. So when you see a periodic table, carbon might say 12.0 something. That's because it's an average. Most carbon is 12, but you have those isotopes. So they average them together, and that's the atomic weight. So radioactive iodine, 131, can be used to destroy cancerous thyroid gland tissue. And it's been very effective, but the thyroid is the only part that transports and metabolizes the iodine, and that's why the radioactive iodine can be used. But other isotopes can be used to look at blood vessels and evaluate kidneys, look at bone density, and the such. And this is just fun to know. Of course, you would not need to know this for a test. But just interesting information. Okay, so a molecule is a particle formed by two or more atoms, and a compound is two or more atoms of different elements. So you might have an oxygen molecule, but a chemical compound is different elements. Molecular formulas tell you what elements are in the molecule and how many of each there are. So for example, the subscript 2 is talking about this hydrogen. So two hydrogens bond together, and that is called a molecule of hydrogen. There's how many carbons in this glucose? There's 6. How many in the hydrogen? 12, and oxygen has 6. That will be important for us later. And then H2O is saying that water is made of 2 hydrogens, H2, and only 1 oxygen. There's an understood 1 right there. And so H2O, sorry, dihydrogen monoxide. Did you catch that? All right, so you can have oxygen and hydrogens, and they can react to make water. And so here you see these water molecules, each with 2 hydrogens and 1 oxygen, and that's why they call it H2O. So we do need to know a little bit about chemical bonding, and this is where the electrons of different atoms interact and form a bond, kind of sticking them together, if you will. And these electrons, as we mentioned, are in these shells or these levels, and the first shell can only hold up to 2 electrons, the second 8, and the third 8. And so they start with the first shell and fill that up, and then they go to the second shell and fill all those electron seats up. Think about them as seats on a bus, and these electrons are going to sit 2 first, and then they're going to go 8 and 8. And it's the outermost shell of the atom that will interact to form chemical bonds. So let me show you what I'm talking about. Hydrogen is the first element on our periodic table of elements, and it has 1 proton and 1 electron. There are no neutrons. Its atomic mass is 1. So remember that, this is the first shell. The first shell can hold 2. In fact, for this to be a stable atom or a stable molecule, it needs to fill this electron shell. Now, helium, it has an atomic mass of 4, 2 protons and 2 neutrons, and it's neutral, so it has 2 electrons. Now, helium, its outermost electron level is full, and so it is stable, and this is why you can find helium as a noble gas. It doesn't react. But hydrogen does react, and so does lithium. Look at lithium. Lithium, the third element, has 3 electrons and atomic number 3 for the 3 protons. And so it filled up its first energy level first, 1 and 2, and now it's working on filling the second electron level. How many can go on the second level? 8. Does it have 8? No. So that means this is very reactive. It's going to form bonds quickly, probably by losing this electron, and then it would fill this energy level. So this is sodium, 11 electrons, 11 protons, so that's even, 12 neutrons, so its atomic number is 23, atomic weight is 23, atomic number is 11 because atomic number is based on the number of protons. And notice it filled its first energy level with 2 first, and then it did 8. 1, 2, 3, 4, 5, 6, 7, 8. Filled all 8 spots up on the second level. And now it's trying to fill the third level. Did it fill it? No. So it's probably easiest to lose this electron than to gain 7. So it's going to be very reactive. Ionic bonds. So first you got to know what an ion is if you're bonding them, right? So it is a charged atom. That means it has a positive sign or a negative sign next to it. How did it become positive or negative? Well, it either lost or gained the electrons. We talked about this already. If you gain an electron, what's your charge going to be? It's going to be negative because you gained a negative thing. And so that would be called an anion, a negatively charged ion. But if you lost an electron, like that sodium we just saw, I told you this sodium is going to lose this electron because it's easier to lose 1 than to gain 7. And so if it lost a negative, now it's going to have more positive things in it than negative things outside of it. So it will have a positive charge and be called a cation. So ionic bonds are these strong attractions between positive and negative ions. And so here we mentioned sodium, and I told you that sodium would rather lose than gain 7. It's easier. So sodium's going to lose and become a positive charge. And chlorine. Look, chlorine filled its first level with 2, second level with 8, and then it has 7 on the outer level. So it just needs 1. So it wants to steal 1, and this one wants to give 1. They work very well together. So this lost an electron and became positive. This chlorine gained an electron and became negative. And what happens when these two get together? Sodium and chlorine. Well, a positive and negative, that's going to kind of cancel out, right? Now, let me tell you something about sodium. If you mix this with water, it explodes. And chlorine steals electrons from your body if you were to breathe it in. This is highly deadly in its pure form because it's very reactive, right? It's desperate to get rid of an electron. And chlorine is desperate to gain one, so it's very reactive. Deadly and deadly. But when you put them together, sodium chloride makes salt. And that's delicious, right? So two deadly things can, when they chemically react and form ions, they're no longer dangerous. They're delicious. So ions are ionic bonds are bonds between ions. Covalent bonds are where atoms actually share these valence electrons, these electrons on the outermost level. And so like two hydrogens can come together and share. Remember, they each had 1. And so if they both share each other's, that will fill their seats on their bus, if you will. And so let's look at some pictures of this. So remember, hydrogen, its first shell, it needs to fill. And so it needs a spot. And so does this atom. So if they share, now you have H2. This is a stable molecule. These are unstable because their energy level's not full. But now if they're sharing, they will be stable. And this is called a covalent bond. Let's look at some other ones. You can take hydrogens, right? Here's H2 and H2. And here's some oxygen. Now, oxygen filled its 2 energy levels, but it only had 6 on the outside. So it's got to share 2 with another oxygen to be stable. So this is like O2, what you breathe. And this is hydrogen gas. You also can take it in. You don't absorb it. And those can actually react to make water. So here's our H2. See them, these covalent bonds, they're sharing pairs of electrons. So this is one covalent bond. The hydrogen sharing its valence electron and the oxygen is sharing its valence electron. So if both are sharing their valence electron, that's one covalent bond. So it takes 2 electrons shared to make one bond. And so these are 2 water molecules. So structural formulas show how these atoms are bonded, and one line is going to be a single bond and 2 lines is a double bond. So here's our hydrogens sharing each a valence electron, so there's 2 electrons there. Here 4 are being shared, right? Sharing of 2, sharing 2 electrons here, sharing 4 electrons between this and 4 electrons between that. And so this shows you what's being shared in covalent bonds. Now, there are nonpolar covalent bonds and polar covalent bonds. And write this next to this, okay? Water is a polar molecule. So nonpolar things don't mix with water. Don't mix with water. Polar things do mix with water because water is polar. So polar mixes with polar and nonpolar actually mixes with nonpolar. If you want to write that out to the side, nonpolar does not mix with water because water is polar. Nonpolar mixes with nonpolar, and polar things mix with polar. Okay, so what is a polar molecule? Well, polar molecules are the uneven sharing of electrons. They are not shared equally in those covalent bonds. Nonpolar covalent bonds are shared equally, okay? And so water, like we mentioned, doesn't share the electrons equally. And so you end up with a slightly negative end over here and a slightly positive end. Like the poles, the North and the South Pole, they're different. So you can think of different charges. I could go into a lot more detail on why this is and help you understand it. But if you draw, these little white parts of the molecule, put H's on those, okay? Those are the hydrogens. This is the oxygen. And if you look at your H, you can make a positive sign out of a H. You cannot make a positive sign out of a O, all right? So that's how you can memorize that. The hydrogen end of water is positive and the negative end is the oxygen. So because of these polar charges on water and other polar molecules, they can form what's called hydrogen bonds. And these are weak attractions between that positive hydrogen and slightly negative oxygens or nitrogens of other polar molecules. And these are pretty easy to break. Water molecules form hydrogen bonds with water molecules nearby. We see this also in nucleic acids and proteins. But look, remember hydrogen has what charge? Positive. So if you want to put a little positive sign here, oxygen has what charge? Negative, and opposites attract. And so that's called a hydrogen bond. And it's always going to be a hydrogen attracted to something else. Either oxygen or nitrogen does this. So chemical reactions occur when these bonds form and break. And we take reactants and turn them into products. So the reactants are what you start with, and then you'll usually see this written as, something, something, in a yield sign, which is like an arrow, the products. The arrow is always pointing to the products. So you can do a synthesis reaction where you build more complex structures. So two simple things make something more complex. You can do a decomposition reaction, so you take something complex and break it down into simpler structures. You can do an exchange reaction, just new bonds are formed, or reversible reactions where you can do synthesis and decomposition back and forth. Both of these can go both ways. Now, I won't test you on all that, so don't put a big X on that slide right there. Won't be tested on that material. All right, I do need you to know what electrolytes. We talk about electrolytes in sports drinks and whatnot. These are substances that release ions in water. And they call them electrolytes because they can conduct electric current. But pretty much these ions in our food and drink are the electrolytes. Now, acids release hydrogen ions. So if you see hydrogen ions, circle the hydrogen right here. That's what tells you this is an acid. Bases don't release any hydrogens. They actually release hydroxide ions. So circle the OH. So if you have a solution that has a lot of hydrogens in it, it's an acid. If you have a solution with a lot of hydroxide ions in it, it's a base. And when acids and base come together, they form salts, like sodium chloride. So this is an acid, hydrochloric acid. This is a base, sodium hydroxide. And when you mix them together, they cancel out into neutral water with some salt in it. So a study of acids and bases measures the hydrogen ion concentration. And when these substances lose these electrons, or dissociate and become ions, that's what calls it an electrolyte. This isn't as important to you either. But what they're trying to say is sodium and chloride can dissociate and then from salt, and they're just now in their ion form. So these would be electrolytes. Okay, what do we need to know on this? Hydrogen ion concentration is measured in our body fluid, and we use the pH scale to measure ion concentration, these hydrogen ion concentration. Okay, you're not going to need to know how many grams per liter are hydrogens to make different pHs, but I do want you to star this section right here. The pH scale does go from 0 to 14, and each step is 10 times the difference, tenfold. So first of all, you can, let's see, I'm going to draw on here, and it won't be pretty, but it'll get the job done. Okay, oh my gosh. So here's my pH scale, and right in the middle is going to be 7. Here's 0, sorry, and here's 14. Okay, so this is neutral, and anything over here is an acid, and anything over here is a base. Look, they're in alphabetical order for you. Isn't that nice? So acids, remember, have more hydrogens. So the further you get away from 7, neutral, like water, the stronger the acid is. So this number, let's say, is a 1, and this is a, oh, I don't know, 4. So there's 1, 2, 3, 4. If we're comparing these, 1 is a much stronger acid. It has more of these hydrogen ions in it. Okay, it's stronger. How much stronger? Well, remember, each step is 10 times stronger. So look, 10 times 10 times 10, 10 times, 10 times 10 times 10 is 100 times 10. This is 1,000 times stronger than the pH of 4. If you go in the opposite direction, the bases get stronger as you go away from neutral or water. And so 8 compared to, oh, I don't know, 9 is how much stronger? Well, 8 isn't stronger than 9. 9 is 10 times stronger than 8. How much stronger is 10 compared to 8? It's 100 times stronger. So think about 10 times 10 is 100. But when you mix bases and acids of the same strength, what will they do? They'll become water. They'll cancel each other out, and they make salt. So this is the pH scale. Oh gosh. Let's erase. Sorry. Okay. And so this is just showing the grams per liter, and this is this is what we drew. 7 is neutral, and as you move higher in number, the base, it becomes more basic. As you go lower in number, it becomes more acidic. So that pH scale does indicate the concentration of hydrogen ions in a solution, like we mentioned. Neutral is going to be 7, where you're equal hydrogen and hydroxide. Look, if you add a plus and a minus, you get neutral, right? And look, H2O, it's water. An acid is always lower than 7, and it has more hydrogens than hydroxides. And basic or alkaline solutions are greater pH than 7, and they have higher concentration of hydroxide ions. And so here's some solutions that you're probably familiar with, and their pHs. And so we talked about distilled water. Pure water is a 7. Look at blood. It's a 7.4. So it's slightly what? It's slightly basic. It has a little bit more hydroxide ions than it does hydrogens. Gastric juice in the stomach, a 2, very acidic. Apple juice, drink a lot of apple juice, it will ruin your teeth. That's why you shouldn't give your baby, your toddler, apple juice all the time, okay? Give them water so that it doesn't eat the enamel away. Please, please, please. Maybe you've cleaned with ammonia. Woo, that stuff's strong. It's a strong base. By the way, acids can burn you, so can bases. Okay, it's just the stronger ones burn more than the lesser ones. So the normal range for blood pH we just mentioned was between 7.35 and 7.45. So they wrote 7.4 right here. Acidemia is when your blood drops to below this, okay, towards the acidic. So look, even though a 7 is not an acid, it's neutral, we call it acidemia because it's more acidic, towards the more acidic side than it should be. Acidosis can make somebody feel disoriented and fatigued, And it could be due to lots of vomiting of alkaline intestines. It could be due to diabetes or other things. Now, the opposite of that is alkalemia. This is where your pH goes too high. And that's alkalosis also kind of causes the same stuff. And we use homeostatic mechanisms to control our pH. There are buffers in our blood and in our body that help chemicals resist major pH changes. And this is why you shouldn't have, notice this isn't a big change, but it causes you to feel really bad. So remember, homeostasis, we want to keep our blood between these two. Now, you've probably heard the term organic substances. Organic substances aren't what you think of like natural in the grocery store without pesticides or what have you. Organic molecules, organic chemistry, are molecules that contain carbon and hydrogen together. And whether they're polar or nonpolar will depend on if they mix with water or not, whether they release ions. Some can be ones that do mix with water won't release ions. And our organic molecules that we're going to study are our macromolecules, these carbohydrates, proteins, lipids, and nucleic acids. So inorganic molecules don't have carbon and hydrogen. They do usually dissolve in water and they'll dissociate, forming those ions. And so they'll form, they're called electrolytes. And so what doesn't have carbon and hydrogen? Well, water, oxygen, and then a lot of people see carbon and think, oh, that's organic, but carbon dioxide is CO2. There's no hydrogen involved. And then sodium and chloride are organic, inorganic salts. So organic, always think about if you see carbon and hydrogen, it is organic. So we're going to talk about the inorganic substances first, and then we're going to pause for a minute, and you're going to go get something to eat something organic, and take a break, and then we'll learn about the organic molecules. So the inorganic molecules, like water, is the most abundant compound in living material. I mean, 2/3 of your weight is water weight, and that's why you'll see people wear those like plastic workout shirts or whatever. It helps them sweat that weight out. Now, once they start drinking again, drinking water again, they'll replace it. But anyway, it's a short-term weight loss. I'm not condoning it. It is where those reactions in our body occur. We need water for those reactions. Remember, water holds a lot of heat and helps transport material in our body. And there is a water balance that exists. Now, water is what's called the universal solvent, which that means everything dissolves in water. We know that's not true, but in our bodies, water is the solvent for most of the things we deal with. What doesn't dissolve in water? Well, nonpolar things. And by the way, nonpolar things are fat. You've tried to mix oil and water together before. They separate because water is polar and oil is nonpolar. Now, oxygen, like we mentioned, is necessary for survival, and the whole purpose of it is to release the energy from our food so that we can live, so our cells can do work. CO2 is the waste product of doing that, and those inorganic salts, here's some examples: sodium chloride, as I already mentioned, potassium, calcium 2+ ions are really important for muscle contraction. Potassium is really important for your nerves to work and muscles to contract. And so they're real important. And if you have an imbalance in those, you do have some problems. And that's why, like, people can get water poisoning. You drink a whole lot of pure water, you lower your electrolyte and it goes out of balance. And some people have been known to die from that. Okay. So that was Intro to Chemistry. The next lecture is going to finish this chapter out on organic chemistry and the macromolecules.